relative. So it really comes down to if the sample size is around 50, and you do your, you say I'm going to do Z because it's easier just by hand to do it, and you calculate your Z, and your Z is equal to 4. Well, it wouldn't have mattered if you did a T, because if your Z is 4, it's so significant it doesn't matter. So let's say you did a Z, and the calculated Z is 1.97. Well, okay, now it's like really close. If you did a T, it's probably not significant. If you did a Z, it is significant. That's where you really have a problem. So it's not. I mean, there's general rules that if you don't know standard deviation, you always use a T, but it's kind of it's a little bit of a gray area there also. Sometimes it's easier to do Z because you can calculate by hand. The critical values in your head, it's significant, and you're done. But when it gets to those, well, maybe it's significant to one and not the other, then you really have to worry about what you're doing. And for all purposes of this class, if you won't know the population, use a T. After this, you may want to sometimes use a Z, and you can have a little more flexibility there. But general rules, you have to follow the class one, test and double back. Did everybody turn in the homework? I'm asking that because if I cover question 14 and you're sitting in class and you come up at the end of class and hand your homework, I'm not going to take it. So, I'm not going to tackle question 14. I'll take the homework in. Good. Valerie, you don't leave, I guess. Okay, homework for you. So for this the homework you handed in last week, there was no. Bring it back. Oh yeah, they handed in last week.
But yeah, with 8.
Yes.
Before it was 7 and 8, and then I just did 7.
So,
But
okay. All right. All right. So question 14. So this question is kind of written a little confusing to begin with. And they tell you that the mean serum cholesterol level of the population of men who do not develop heart disease is 219. So first thing you might be thinking, okay, that's going to be my null hypothesis. Well, it's really not. And they say the standard deviation is 41. So we believe we know the population standard deviation just in general. Yeah. Well, I said you would think that it's your null hypothesis, but it's really not. That's going to be the alternative. And that's why it's kind of confusing, because they initially write it as if that's your group that you're comparing against, but it's really not. And then they give you this kind of, as you said, they kind of say, well, you know, but maybe you really don't know it. So, which is kind of confusing also. So suppose, however, that you do not know the true population mean, and instead you hypothesize it to be 244. So that's the mean of the serum cholesterol in men who eventually develop this disease, and that's going to actually become our null hypothesis. So then they say that we believe that the mean serum cholesterol level for men who do not develop heart disease cannot be higher than the men who actually do, so they actually going to do this as a one-sided test. And that makes sense. So it's just going to be a one-sided test. You're going to use an alpha of 0.05, and they say the first question is, what is the probability of making a type 1 error? Yep. If you have homework, bring it up, because we're looking at question 14 right now, so you have to hand it in. No, that's going to be the null. They say that men, they believe that the mean serum cholesterol level for men who do not develop heart disease cannot be higher than that value. And the value you're going to be comparing, if it can't be higher, it has to be less. That's your alternative, that it's less. The alternative is that it's less.
Okay. But this is already given as less, 219, right?
No, it's going to be less than 244. You have your
And that's what we are saying, that it has to be less than 244, and that's what they are giving like 219, and that is less than 244. So isn't that clear from the question itself? So it's not really wanted that.
Well,
Like,
so,
basically it was like mu is equal to 255, then we can test it against that it has to be lower, not higher than 245. But it is already given as lower than 244.
so what, but they're saying, see, that's the confusing part. They're saying they've given this 219, but then they say, well, suppose you don't really know it's 219. All you know is that the mean value in the men who develop heart disease is 244, and you're trying to determine, then you're trying to test for the people who don't have heart disease, and you're saying, well, for the people who don't have heart disease, it has to be less than 244.
Right.
That's where it's your alternative. Assume you don't even know 219.
Right, okay, so in that case, what would be assume that, like, mu minus mu 0 will be 244, then what will be mu in that case?
Mu 0 is 244. The alternative is that mu 0 is less than 244.
Yeah, so when we calculate the z for z or t statistic,
Well, so that's down the road. We're talking about the alternative hypotheses right now. Okay. So the hypotheses are mu is 244. That's the null is that mu is 244. The alternative is that mu is less than 244.
It was worded kind of funny because it said that,
Oh, yeah, obviously it is worded funny. I'm not debating that.
okay, but it was saying, okay, so pretend that you don't know this and that it's 244 and then it said this is the, so I thought that they were saying that 244 is the one, the two sentences don't agree with each other.
Sure.
It says,
I'm not debating that. So what I'm telling you is the mean is 244 and the null hypothesis, and they actually give you in question E, part E, they actually give you what the null and alternative are. So they've spelled that out for you. So even though they've kind of been confusing, they've spelled out what the mean and alternative are. So let's look at it. So the first question is, what's the probability of making a type 1 error? So the probability of making a type 1 error is regardless of the null and alternative, they've given it to you by what the alpha is. So the probability of type 1 error is equal to what? 5%, yeah.
but didn't we talk in the class that the actual probability is the one that we calculate from the t statistic?
Right, but we haven't done that. So all they said right now is alpha is 0.05, what's the probability of type 1 error? You haven't done the test yet.
But they said that they did that like in the last sentence, there is a one-sided test. So it happens that, right?
No, you're going to do a one-sided test. So the first question is, what's the probability of type 1 error? You haven't performed the test yet. All you said is alpha is 0.05, we're going to do a one-sided test. Before I've done the test, what's the probability of type 1 error? 0.05. You haven't done the test. So when you're on a test, if I give you a problem and I say you're going to use an alpha of this, and I ask you what's the probability of type 1 error, it's equal to alpha. You haven't done the test yet. Once you've done the test, then you know exactly the probability of type 1 error is for the test that you've done. So beforehand, it's alpha is 0.05. That's the probability of type 1 error. Before you do the test. Once you've done the test, then it changes. So the next question is to say if a sample size of 25 is selected from the population, what is the probability of making a type 2 error? So this is a little bit tricky because we never really went through this in the lecture. So I was talking with a couple of people. This is the first time that 2 people actually came to my office hour. This has never happened before. Never one person, never 2. The question is, how do you actually go with figuring out that problem? The textbook figures out the problem. The textbook actually does it. So if you went to the textbook, it would tell you how to do it. I'm going to show you an easy way to figure that out right now. It's going to be the area on the graph to the right of the alpha level and the alternative hypothesis. Yeah. But two distributions. We have our alternative distribution here, 219, our null distribution, which is 244. Now you actually have to go back and take that 219 value because that's what your alternative is going to be. You can only figure out power and beta and all those if you specify what the alternative is. Because unless you do that, you don't know where this alternative distribution has to be. You have to specify it somewhere. So we're doing this as a one-sided test. And when you do any type of a test, this is your formula for your Z. What we're trying to do is figure out where is this score in regards to our original data. So we can figure out where this is in regards to a Z. We know where that is because we know if we specify what alpha is, we know exactly what that Z is, and then we have to figure out, well, what value of X does that actually correspond to? So since it's a one-sided test, we know that it's going to be 1.645. That's the critical value for a one-sided test at alpha 0.05. We also know it's going to be negative because the alternative is going below. The alternative is less than. So what I am trying to solve for is x bar. Once I have then solved for this value of x bar, I can say, okay, well now that I know what that value is, I can figure out, given that the alternative is 219, what value of z does that correspond to in this distribution, and then I can figure out the area to the right of that score.
Would 25 be the number?
Yes, 25 is the sample size. Yeah. So, using some... divided by 5 is 8.2, so x bar is equal to negative 1.645 times 8.2 plus 2.4. Because the alternative was negative, so we're only interested in, and as you see as I drew it, I had to actually draw these, so this is the knee, it's on the negative side of the knee, so it's negative. If it had been two-tailed, it'd be negative 1.96. Well, and the first thing is you want to draw this out. Draw your two distributions. Because the alternative we know is on the lower side, this is going to be on the lower side of that, which means it's below the mean, which means it's negative. This is, as a z-score, this is 0. This is going to be negative. If it was two-tailed, I'd have 1.96 here, negative, and I'd have 1.96 there, positive. But when we're actually calculating power or anything like that, we've got the 1.96 on both sides for two-tailed, but then we don't even worry about that anymore because we specified that the alternative down here is only calculating on this side. Okay? So it's one-tailed, 1.645, and we know it's negative because it's below here. And so it's negative 1.645 for this distribution. It's going to be a positive number on this distribution here, which is what I'm calculating now. Negative 13 plus 244. is the value, that's this value right here, and this distribution, it's value of 230.151. That's what the value is in both distributions. So that negative, this negative 1.645 in regards to the z distribution corresponds to 230.151 in the original distribution.
I guess when I was doing that problem, I got the null hypothesis and the alternative hypothesis opposite, and so I actually got positive 1.645. Can you just go over why it is the way you got the two hypotheses? I mean, besides the fact that it's given an E, because it's not mentioned anywhere else.
Because they actually say that we don't know what 219 is, and then they say, however, you hypothesize that u is equal to 244. So that's what they're saying. You're hypothesizing that the mean is equal to 244.
That's not what they said. They said, suppose that you do not know the true population mean. And then they tell you the 244, and then they say that this is the initial serum cholesterol. So they're not saying that you don't know the 219, they're saying you don't know the true population mean. And
They
they're not
say you
letting you know which one
hypothesize
is.
that mu is equal to 244.
Yeah, but they're not saying which one is the true population mean, and so that part is based, whichever way you want to interpret it. It could be interpreted either way.
If you did this, my belief, and I'd have to calculate the numbers, if you flip this around, if you reverse these two and did the exact same calculations, you should come up with the exact same power.
No, we don't. We did it the other way.
And I'm wondering if you made a mistake in the calculation.
A lot of us did the calculation.
Okay. I will check that in a second.
Okay.
So now you get this value of 230.151, and you have to figure out what kind of z does that correspond to. So I just put 8.2 there because that's going to be the exact same thing as 41 over the square root of 25. So we get
$1.40.
1.3598. So we have to go into our z table to find out what that value to the right of that is. .36 is 0.087. So that would be beta, 0.087. That's okay. In the exam, how would I mark it in the exam? You get a lot of marks, but I might take off half a mark because you didn't do enough rounding possibly. So I guess two things. So here you use 1.65 instead of 1.645. So yeah, in regards to exam questions, if you, instead of using 1.645, you use 1.65, and then you possibly can carry as many decimals as you went through it. You got something a little bit different. I would possibly take off a quarter or a half mark out of something that's worth maybe 5 or 10 marks. So it's important when you're doing your calculations that you don't just take a shortcut over time and only keep one decimal and end up with something different. So make sure you keep 2 or 3, 3 decimals. When you're doing calculations, you've got a calculator. You should have a calculator. You can keep all kinds of decimals. 4 or 5 decimals isn't gonna make any difference, but if you start rounding down to 1 decimal, and do your calculations based on 1 decimal, you do 5 or 6 calculations, all of a sudden you're gonna get a slightly different answer. So you have to make sure you keep a little more precision when you're doing calculations. So the majority of things is to make sure you understand what you're doing. When it gets down to the final answer, I think with the final answer, if instead of having a value of 0.087, which is what this corresponds to, and you had something like 0.081, I know you've done some rounding error somewhere, and I go back and try to figure out where that went, and see whether it was just something you forgot or not, and you might lose a quarter or a half a mark out of something which is worth 5 or 10, depending on how it went. In that case, then I probably wouldn't deduct anything for that. I guess I'm not completely following. If we flip these, we can, I'll do it, I'll flip them and we'll go through the same calculations. So that's probably just rounding stuff. So unless I did something wrong in my other calculations here.
It's 230.51.
Is it? 230.5? So, but it would be, depending on what you use for your that, I use 1.645 times 2, there's 13.48 now, and I subtract that from 4. Oh, 2.45. Yep. So that should be. Correct, that's on stage. It's going to be a little bit different in regards to
0.07.
40. So it's 0.081. And 10.404 really drops closer to 0.081. But it, okay, so there's two things. 1.404, which is what that works out to, right?
1.408.
1.402. So 1.402 is still going to be 1.4. 0.402, it can't roll, it won't round to 1.41. It's 1.40. So if you take a look at the table, 1.40 is 0.081. I wouldn't get too concerned about that. When I'm marking them, it's going to depend on So it's two things, when I'm marking your problem, as I go through it, I'll have a certain type of attitude as I'm marking your problem. I'll be looking at it either knowing, one, you knew what you're doing, or two, you had no idea what you were doing. And that's gonna be based on, as I look through your problem, whether you set up all the alternative hypotheses correctly, and as I go through it. So some mistakes that you make, if you know what you're doing, are gonna be looked on less grievously than if they're looked at as I'm going through, if you didn't, like I said, you didn't know what you're doing. Because then I figured you made the mistake because you didn't know what you're doing versus you made the mistake because you looked at the table and you said, okay, I got it, that's 0.41, that's what I'm trying to say, right? So depending on how you're doing on the problem, I may or may not even worry about that. So if you do everything correctly and you get to the end and you get 0.079 versus 0.081, the odds are if you did everything exactly right, I'm just going to say it's a fraction of 0.481 and I'm not going to take the marks off. And that kind of gets down to just a sense of, you know, I'm not going to be going through there looking for little picky things to make issues with. That's what I'm marking. I usually do that. So if I go through it and I see that someone's only keeping one decimal when they get to the end, they kind of, their answer's way off, I'm going to take some marks off because you didn't do proper rounding when you do your calculations. Yeah, if you kept all your calculations in there and at some point you just made a real big mistake, I'll take something off also. If you kept all your decimals in there and you made some little mistake in the end, I probably won't take anything off. So it's going to depend on what the mistakes are and how they all work out. Bigger mistakes when you get the test, when you're doing kind of a test, not so much like this, because this isn't a test, but at the end of this, when it comes down to conclusions, once you've done your significance test, when you get to the end, you have to make some sort of a conclusion, and the p-value is significant, and then you say, and then we retain the null, you're going to lose some marks there because that's a big interpretation error versus a small calculation like this that really doesn't do anything at all. So, it's,
But in the exam, you are not gonna say that it's confusing.
no. So if we're doing it the other way, we're trying to figure out this is alpha and this is beta. Okay. So it's going to be Q19, it's going to work with the exact same value, right? No, works out to be a little bit different. 32. So then I have to figure out right? This should give you the exact same beta and plus minus beta. Beta, so this works out to a value of, so in this distribution it was 165. In this distribution over here is a negative 1.404. Beta is the area to the left of that, which is going to be the same as before, 0.081. That worked out. So what did you guys do that was not correct?
We got the same answer.
We got this same answer, we just didn't get the same answer you had before we made the mistake, so.
Oh, okay, oh,
This
okay.
works
idea that you should understand how you're handling these issues. Always draw your two distributions. And past tests, I haven't had anything that difficult. Calculating sample size, yes. Calculating beta, I haven't done anything like that in past tests. Is that the hardest thing in that question, or is there any questions about that question? Question 14. Yep. Speak up, sir. Alpha is false positive. Alpha false positive. False positive is